Now to the fundamentals. At the end of the day, all we're trying to do in wastewater treatment from a biological perspective is we're trying to take organic material that has carbon and leverage the metabolism of microbes. Exposed to a carbon source, microbes are going to consume that carbon source. That treatment is either going to happen aerobically or it would happen anaerobically. If it happens aerobically, our end products would likely have a significant amount of CO2, and we will always form some excess sludge. If it happens anaerobically, our main output will have methane. There will also be a little bit of CO2, but we will also have some sludge, less sludge, because the anaerobic process, is energetically less efficient, which is an advantage for us because that generates less sludge. At the end of the day, that sludge would have to be treated. So the less sludge we have, the better. Anaerobic processes in general tend to provide a lower yield relative to the amount of COD, the chemical oxygen demand that is reduced. So we know microbes are effective. We know they're extremely effective. We know they can remediate a broad range of contaminants. And one of the and if you look at the pros and cons of the process, the main advantage of the biological approach is we're leveraging nature. Microbes were here on Earth long before humans came here. They have learned to metabolize most things. There's practically nothing that microbes can't deal with. The only challenges we're facing now are some new molecules we've created. So things like PFAS are a little difficult for microbes to deal with because they're new molecules. We're just starting to find microbes that can metabolize some of those materials. We're finding it a little difficult to have microbes that can metabolize things like artificial sugars, for example, in wastewater treatment systems, because these are new. They're new challenges to microbes. But interestingly, we're also starting to find that there are microbes that have started to adapt. So when you look at some wastewater plants, and I did this work in the last 5 to 10 years, we were seeing, things like aspartame and some of these new sugar molecules, sucralose, just going through the process almost completely untouched. But now we're starting to see microbes adapt to them. So microbes are remarkably adaptable. So the beauty of the process is it's cost effective, it's robust, it's flexible. Any wastewater treatment plant, we do a lot of genomics. There's thousands of bacteria. If one fails, there's another that's going to take over and get the work done. And then obviously it's publicly accepted. Disadvantages, though, is that it's not everything that is biodegradable or readily biodegradable. So take your typical sewage. Roughly half of what the biggest portion of what we excrete is what comes out of a home is actually solid. So 50% of our sewage waste in a house is actually it's solid material. Now that solid material is biodegradable, but it's going to take time for that biodegradation to take place. It has to be hydrolyzed. A microbe can't feed on anything bigger than itself. So if a microbe is about 0.1 to 1 micron in size, then it means those large particles that we're excreting, that are 100, 200, 300 microns in size, that make up those undigested food materials or make up other microbes, they have to break down. They have to become solubilized. It takes time for that to happen. So we're challenged by the fact that not everything is biodegradable or readily biodegradable. It has a big impact on what we're able to do and the timescales. And a lot of the challenges we found is, although microbes are effective, extremely effective, that I love to look at this image. The microbe can't do treatment unless the food material, the material we're trying to treat, somehow passes through this cell wall. In order to pass through this cell wall, there are all types of challenges you need to have. First, it has to be small enough to pass through, so it has to be solubilized. But the second thing is that your mass transfer systems have to ensure that you are moving material from areas of high concentration to areas of lower concentration. You are bringing it close to the microbe, which requires, in some cases, movement. the ability to be able to put some motion around the microbes to transport those materials. So remarkable process, but then we're also some issues we have to deal with. And then just the dizzying array of microbes and functions that we require. If we think about just sewage, what's coming from somebody's home, the challenges we face are immense. So we have carbon. In order to degrade carbon, we need things like traditional heterotrophic biomass. We need facultative organisms. A lot of organisms are facultative, especially a lot of the organisms that are in the human digestive system. So our digestive tract, about half of fecal matter is microbes. Those microbes are mostly anaerobic inside of the human body, but they're facultative. So exposed to an oxygen-rich environment, those microbes can also metabolize. But in order to just treat what's coming out of a human body, we need facultative and heterotrophic organisms to do COD removal. We need fermenting microbes to be able to help us break down some of those large molecules and help hydrolyze them. We need methanogens to take the products of that hydrolysis that have been turned into volatile fatty acids and convert that into methane. We need nitrifiers to take the organic nitrogen, which is in a bound form, and convert that into nitrates, because the only way nitrogen is treated is to convert it to a gas. That's the only way we can treat nitrogen. So how do you do that without doing some type of nitrification that converts organic nitrogen and ammonia into nitrates? And then we have other microbes, a lot of them heterotrophic, that are then able to take those nitrates and degrade them and use and basically use the oxygen from those nitrates in terms of reduction. We have ion-reducing bacteria, and in the industrial context, there are many of these bacteria systems that we've dealt with. You also find them a lot in digestion type systems. Halophiles, we do a lot of work, especially on the coastal area near the oceans, where there's a lot of seawater infiltration. There's a lot of halophiles, high salt tolerant organisms that need to be involved in the wastewater treatment process. Otherwise, those treatment systems are not going to be resilient because they have all this seawater infiltration and quite high levels of salinity. So just a dizzying array of microbes that we have to deal with. And these microbes, they provide resiliency, but they also provide challenges because each of them has a very different kinetics. Their growth rates are different. The environments and conditions they like are different. The halophiles like high salt environment. The alkaliphiles like high alkalinity. Many neutrophiles want to stay in a neutral range. All of these different conditions have these immense impacts on microbes. And what I've learned over the last, in my time serving in this space, I've just been the fact that there are these 8 factors that determine what our microbial consortia looks like. Many of these factors we actually don't have any control over in wastewater treatment. We don't have any control over the food. The food by definition is waste. So this is not like a brewery where we're feeding the microbes specific food and we're choosing what we feed them. It's wastewater. Today it might be fats, oils, and grease. Tomorrow it might be proteins. The day after it might be, it might just be some spillage that falls, that falls through the sewer system. So the type of food we have is variable. The temperature can be variable, especially in places like the US where, it could be, it's in Chicago, it might be minus 21 day, the next day, but the bugs require the environment to be at about 25 degrees Celsius on average for them to function well. The retention time varies. It can vary just based on the fact that you have fluctuations in flow to a plant. If you have wastewater systems that are not separated from rainwater, the volume of material that's going in can have a 10x variation. So hydraulic retention time changes. We have plants that have small hydraulic retention time, some have longer retention times. The oxic environment, the ORP conditions, the nutrients that you have. In some instances, especially municipal sewage, we have all the nutrients we need, because it turns out that what we feed on is also the same thing, is very similar to what the microbes want to feed on. So they have the nitrogen, the phosphorus they want. In most cases, we're trying to remove nitrogen and phosphorus. In the industrial context, there's almost always carbon, no nutrients. So we're actually needing to add nutrients. We're needing to add nitrogen, needing to add phosphorus to those industrial systems. The sludge age, it varies. If all I want to do, which was what we did for the first 60 years of wastewater treatment, if all I want to do is remove carbon, all I need is about 2 days of retention time. The average age of my bacteria doesn't need to exceed about 2 to 5 days in order for me to have effective, almost 100% COD removal. However, if I want to do nitrification, if I want nitrifiers to grow in the process, I cannot do that unless my average sludge age, the retention time for those microbes, exceeds about 5 to 10 days. In fact, sometimes up to about 15 days, because they grow more slowly. So that's a complication, because now it means, I need to find ways of retaining microbes, which means I might need to increase the size of my basins, or it might mean I need to hold more material in inventory. And then the pH and the alkalinity, microbes are extremely sensitive to the pH, to all of these conditions. And we cannot always guarantee we would have this condition. So what options do we have? Well, bioremediation tends to be one thing we could do. So nature does whatever nature wants to do within the treatment system. And then one of the things I've learned to do over the last 10 years is leveraging microbes, identifying how best we can optimize the tools we have, and then tapping into nature. So if what I need are nitrifiers, then maybe I don't need to build bigger basins to get the nitrifiers. Maybe I just go back here and find some nitrifiers in nature, cultivate them someplace else, and then bring them into the process. If I need, so maybe what I need are halophiles. I probably don't need to expose my entire system to halophiles. I can see whatever hand nature has dealt me in my process, optimize it as best as possible, and then go find halophiles and bring those halophiles into the system.